My name is Justus Piader. I'm from the University of Innsbruck in Austria. This session is essentially about building accurate models for estimation and control. And the first talk will be about differential particle filters, allowing end-to-end optimization of state estimation. The second talk about learning locomotion strategies in simulation, and the authors invest a lot of work into closing the reality gap between simulation and the real world. The last two talks of the sessions have to do with biomedical signals, but in very different contexts, but both about state. So the third talk is about adding haptic feedback in terms of stiffness to an augmented reality system for surgical interventions in simulation and in real time. And the fourth talk will be about combining EEG and EMG signals for intuitive and abrupt intervention in exceptional situations in human-robot interaction. So our first speaker is Rico Jankowski, and he will talk about differential particle filters, end-to-end learning with algorithmic priors.
Thanks. So deep learning is taking robotics by storm right now. There are methods for both perception and control that don't rely on classic robotic algorithms. But does deep learning make past robotic research obsolete? Let's look at the particle filter algorithm, for example, which is a classic algorithm for state estimation in robotics. Will we stop using this algorithm in the future and just learn everything with deep networks such as LSTMs? I don't think that's a reasonable approach, because particle filters make a lot of useful assumptions about the problem. For example, that what we want to filter about is a belief over states, and that we can split up the filtering process into a prediction and a measurement update step. LSTMs don't make the same assumptions, but they're differentiable, so we can learn all their parameters to optimize end-to-end performance. But what if we could combine these two approaches? What if we could get the best of both worlds, get the algorithmic priors encoded in the algorithm, but also get the differentiability from LSTMs, and therefore can optimize everything for end-to-end performance? So we did this in our paper, and the result is called the differential particle filter. So the differential particle filter is basically just a particle filter implementation in TensorFlow with learnable models. So because everything is differentiable, we can apply the particle filter to a sequence of observations and actions, and we can compare the output to the true state. And then we can backpropagate the error to get a gradient on how we need to change the models to optimize state estimation performance. And this leads to a number of advantages. So from the end-to-end learning, we're able to optimize the models for state estimation performance. So we will get lower error rates. From the algorithmic prior, we get advantages such as explainability, improved data efficiency, and improved generalization. And in the next 2 or 3 minutes, we will look at all of these claims. So we applied the differential particle filter to a task of learning to localize based on RGB images and odometry in a 3D maze such as this one. So here you see a simulated robot randomly walking through a maze, and its task is to estimate its position and its orientation based on the stream of RGB images and odometry. So let's look at what the particle filter has actually learned. So let's look at the output of a learned particle filter during one estimation run. So the red thing you see is the ground truth robot pose, and all the other arrows show the particles that are outputted by the particle filter. And their color denote the weight of these different particles. So in the beginning, the particles are all over the place because the filter doesn't know where the robot is. But then over time, they start to form clusters. And these clusters, after a while, they collapse on one cluster, which just tracks the true position of the robot. And this is all with learned models on RGB data again. So we can see that it works, it learned the right thing. But how does it perform? How does it compare in terms of performance and data efficiency to just a normal particle filter and an LSTM? So here we look at the learning curve, where the x-axis is the amount of data on a log scale, and the y-axis is your error rate, so lower is better. So if we look at the baselines, one of which is a particle filter with individually learned models, and the other one is an LSTM, And then we see that the DPF outperforms both of these baselines by a large margin. And it works better with small amounts of data, but also works better with large amounts of data, reducing the error rate compared to LCM by about 80%. But then what we're also interested in is generalization. So a learned localization don't just need to work on a specific way the robot moved during training, but it needs to work independent of how the robot moves. So here what we looked at is what happens if we change the way the robot moves through the maze. So we looked at two different policies, policy A and B, and we trained and tested with both combinations of these policies. So if you train and test with the same policy, we see that all methods work well. But if you change the policy during testing, we see that LSTM jumps to very high error rates of over 80%. The LSTM basically overfitted to a specific way the robot moved through the maze. The algorithmic prior in DPFs prohibits this because it cannot overfit to the way the robot moves. So we saw all these disadvantages of combining particle filters and end-to-end learning. But we only showed this for one algorithm. And there are many other algorithms. So let's make all algorithms differentiable, and let's combine the best of both worlds, algorithmic priors and end-to-end learning. And if you find that interesting, all our code is on GitHub. The link is here, but also in our paper. And I would love to talk to you about this at my poster this afternoon. Thanks.
Our next speaker is Jay Tan, and he'll talk about sim to real, learning agile locomotion for quadruped robots.
Good morning, everyone. My name is Jay Tan from Google Brain. This is a collaborative work between Google Brain, X, and DeepMind. The majority of the land on Earth is not paved. In these situations, legs are far more effective than the wheels, no matter it is in the wild or at our homes. However, designing locomotion controllers for these leg robots is a non-trivial task. Traditional approaches rely heavily on expertise, experience, and tedious manual tuning. Can we automate this process? Can a leg robot learn to run by itself? Recently, we have seen tremendous progress in deep reinforcement learning. These methods not only beat the best human Go player in the world, it can also learn locomotion controllers in the simulated environment all by itself. However, there are a few challenges to apply these methods to the real robot. First, having some control over the learned gait is important for robotics. However, deep reinforcement learning does not provide us with many control knobs. The best thing that we can do is to shape the reward function. However, this is not intuitive and sometimes require a lot of tedious manual tuning. Second, most of these methods are exclusively evaluated in a simulation. As we all know, a controller that works in simulation may not work well at all in the real world. This is known as the reality gap problem. In this project, we tackle both challenges. We designed a system that has two components. We first implemented an accurate physics simulation using PyBullet. Then we applied reinforcement learning techniques in the simulated environment so that the simulated robot can learn fast, stable, and energy-efficient locomotion gait. More importantly, we have narrowed the reality gap so that the policy learned in simulation can be successfully deployed to the real robot without additional fine-tuning on the physical system. Reinforcement learning optimizes a policy that maximizes the expected return. To enable user control, we decompose the action space into two parts, an open-loop reference trajectory and a feedback controller. The user can specify the reference trajectory to express the desired gait, and then the feedback controller is learned automatically to modify this reference trajectory so that the learned locomotion is stable, fast, and energy efficient. This gives the user the full spectrum of controllability. On one hand, the gait can be fully user-specified. On the other hand, if we set the reference trajectory to 0, the system is learning from scratch. For example, this galloping gait is learned purely from scratch. By balancing these two components, the user can decide how much control or prior knowledge are put into the learning system. For example, by specifying a few simple sign functions, it can guide the learning system to converge to this trotting gait. Unfortunately, due to the reality gap, if we deploy this policy to the real robot, it falls immediately. To narrow the reality gap, we first improve the simulation fidelity. In addition to thorough system identification, we find that the actuator model and the lack of latency handling in the simulation are two major causes of the reality gap. In addition, we randomly sample the physical parameters in the simulation and add a lot of perturbation forces to the simulated robot during training. This learns a more robust controller that ease the transfer from simulation to the real world. Last but not least, we find that the design of the observation space also plays an important role to overcome the reality gap. As a result, the robot can gallop or trot in the real world. More importantly, we find that the learned gait is far more energy efficient than handcrafted gaits by the expert. In summary, can we automate the design process of locomotion controllers? I believe that, yes, we can. In all above examples, the locomotion gaits are learned automatically within a few hours of computation. To know more about this research, please come to talk to me during the poster session. Thank you.
Our third speaker is Nick Zavalos, and he'll talk about a real-time augmented reality surgical system for overlaying stiffness information.
Hi, I'm Nico Ceballos. I'm the artist in residence here at the Biorobotics Lab at Carnegie Mellon. And I'm going to present our paper, A Real-Time Augmented Reality Surgical System for Overlaying Stiffness Information. Whew. And so first I'm going to start with stating our problem, which is that what we'd like to do is register our phantom organ, in this case a silicone prostate with an embedded stiff inclusion, and register that to the user's view and to the robot's workspace so that we can probe the organ in 3D using our robot, using a miniature force sensor, and showcase our state-of-the-art tumor search algorithms, display that stiffness as a registered stiffness map in the user's 3D view, and keep everything cheap, modular, and reproducible. This last point's important because we have collaborators at Johns Hopkins and at Vanderbilt, and what we'd like to do is have them be able to plug in their own sensors, their own algorithms very easily, and have it all be plug and play, as well as testing it in multiple environments. So there's been a lot of work in this field, including on force sensors, surgical registration, stiffness estimation, and also augmented reality in the surgical space. These are almost fields within themselves. But there's also been combinations of all these work, but all these works tend to focus on either flat or semi-flat organs. They use external force sensors a lot of the time, and they overlay the stiffness information in a non-intuitive sort of 2D space. So our assumptions are that the organ won't move or globally deform when we poke it, that we have an accurate 3D model of that organ a priori, and that the robot does what we tell it to. So the steps that we're going to take is first generate a a point cloud using our stereo cameras, and then we're going to register our preoperative model to that point cloud, and finally we'll use that registration to display that stiffness to the user in their viewpoint. So this is what the user would see while using our system. They first select out the organ that they're interested in. You can see it masks it out. We're using very built-in things to do that. But this is our registration algorithm, which is very fast. And so now that it's registered, they can select an area on the surface of the organ that they'd like to explore. And the robot will automatically, using our smart tumor search algorithms, search on that organ by probing it along the normal of the surface. So you can see it probing in 3D all over the organ. And it'll be smart about which points it chooses to probe. And here you can see the final, in real time, stiffness map being updated, and the left side is the left image, and the right side is the right image. So with your eyes, you're able to combine these into a 3D intuitive look. So our magic sauce basically is to use existing sensors as much as possible, including our stereo cameras, using robust registration methods to make up for those bad, noisy point clouds, and to use efficient search algorithms to make up for the slowness of our robot. The registration algorithm we use is called Bingham registration. It was developed by us here at Carnegie Mellon, and it's very robust to initial guess errors, so we're able to register without any sort of user interaction, and it's fast enough that it works in real time. Our force sensor that we use is very small, which means that it doesn't interfere with the tool of the robot, and we can work with the same workspace. It's $10, so it's basically disposable, and it can sense forces in 3 axes. The tumor search algorithms use algorithms such as LSTM that, again, were developed in-house with collaborators. And these algorithms are able to very quickly find multiple tumors, locations, and shapes. So you can see here, it'll find the second tumor right there and display it to the user. So our augmented reality system is very similar to other augmented reality systems. You can not only display stiffness, but also put in annotated organs, such as the one you see. So our results, finally, on the far left, you can see a raster scan that we did over about 90 minutes with a $6,000 sensor that has hundreds and hundreds of points. And then our result, which uses about 15 points and took about a minute. And you can see on the far right, you can see that we're probing along all those green lines, those green normals, and we're probing the full 3D space of the organ. So in the future, we'd like to deal with physiological motion and all sorts of other neat stuff. But I encourage you, we're right downstairs if you want to come by and see the robot and the system. All our code's open source and available online. And yeah, we've got a poster coming up, so check it out. Thanks.
Thanks, Nick. And our final speaker of the session is Joseph Del Prado, and he'll talk about effective plug-and-play supervisory control using muscle and brain signals for real-time gesture and error detection.
Hi, I'm Joseph Del Prado from MIT, and our work uses brain and muscle signals to supervise robots. As robots become more common in factories, classrooms, and even homes, it's important to communicate with them effectively. And rather than use explicit commands, we'd like to use nonverbal distress signals or gestures the way we do when talking with other people. This is especially important in safety-critical scenarios, where we want to detect and correct mistakes before they actually happen. Our work looks to address this by combining 2 streams of biosignals. We use brain signals to quickly detect mistakes, and muscle signals to actively correct mistakes. The system we designed to test this approach mimics a factory robot choosing from 3 drilling locations while a human supervises. If the person thinks that the robot chose the wrong target, this is detected in their brain signals, collected via EEG, and the robot stops to ask for help. The person can then gesture left or right to scroll through the possible targets using their muscle signals, collected via EMG. Once a target is chosen, the robot can operate autonomously again. This builds on previous work for using EEG to detect errors, EMG to detect motions and gestures, and multiple signals for hybrid control. Since these signals can be noisy and hard to interpret, experiments are usually controlled and retrained for each new user. Our current system creates 2 pipelines to classify biosignals. Brain signals are processed at key decision points to detect errors quickly and without requiring the user to learn any new behaviors. Meanwhile, muscle signals are processed continuously to detect left and right gestures to provide more refined and active control. These 2 streams are then combined into a hybrid control framework for fast and reliable supervision. The algorithms are also designed to be plug-and-play, so the system does not need to be retrained for each new user. Experiments were then performed with 7 untrained subjects and divided into 2 segments. The first segment was open loop and focused on testing the EMG system by cueing specific gestures. The second segment was then closed loop and used the EEG and EMG systems together to provide real-time supervision of the Baxter robot while it performed the target selection task. The EEG classification algorithm looks for signals called error-related potentials. These are generated unconsciously in the brain whenever we notice a mistake. They're known to have a characteristic shape and to occur in a central region of the brain. So we choose 9 central electrodes from the EEG cap, we filter them, and pass them to 2 neural networks in parallel. To keep the system plug and play, we only train on data from previous users of the system. The outputs are then combined to predict whether or not an error-related potential is present when the robot chooses a target. If no mistake is detected, then the robot can just continue operating autonomously. But if a mistake is detected in the brain signals, then the robot immediately stops and asks for help. And at this point, we want to use left and right gestures to choose a target and control the robot. So we collect muscle signals from the inner and outer forearm using 2 EMG electrodes. These signals are filtered, envelope detected, centered, and also normalized to help deal with variations over time and between subjects. And since we want to do continuous classification without knowing when a gesture will occur, we also need to be cognizant of how sensitive the algorithm is to shifts in time. And for this, we use data augmentation on the training examples. For each example of a gesture, we move it a little bit to the left and right and label these as additional good examples of the gesture. But we also move it farther to the left and right and label these as bad examples. Together, this is meant to encourage the network to prefer gestures that are centered in its classification window. We can then use this augmented corpus of examples to train a single-layer neural network. And as before, we only use data from previous subjects to keep it plug and play. The classifier was then tested when subjects were cued to make specific gestures, and we were able to detect over 93% of the gestures online. We also saw a relatively consistent performance across all subjects. The same classifier was then used when subjects could make either gesture at any time they wanted. And here, we detected about 75% of the gestures, with the most common failure case being missing gestures if too many were made very rapidly back to back. There were also very few false positives, so the robot rarely stopped due to muscle signals if the person didn't intend to make a gesture. This EMG pipeline is then combined with the EEG pipeline for the full hybrid control system. Since the EMG classifier operates continuously, gestures can be made at any time after a mistake is detected in the brain signals, or even to interrupt the robot if necessary. Using these 2 streams together, the brain signals provide a way to detect errors quickly and unconsciously, while muscle signals provide more refined and reliable control. The supervised robot was then able to choose the correct target in 97% of over 1,000 trials. So overall, the EEG algorithms for detecting mistakes can be combined with the EMG algorithms for correcting mistakes to create a hybrid supervision framework that is also plug and play for new users. Thank you.
So we have some time for questions, and I ask all 4 speakers back onto the stage while you guys think of questions to ask. Over there, the orange microphone.
I have a question for Rico. Firstly, I'm over here. Okay. Firstly, really interesting idea, and thanks for the talk. Is there a particular challenge with making this work in like an outdoor real environments here? Because if it's in simulation, you're trying to simulate various sensors, which can be typically quite hard to simulate, I guess. Well, if you're getting real data, you need supervised real data of outdoor estimation of like accurate estimates, and I feel like that could be challenging too. So I know the reality cap is always there, but I wonder if it's particularly challenging for this kind of scenario.
So we did apply it also on a real-world data set, which was the kitty data set, where we learned tracking. But yeah, so right now this method needs supervised data to learn it. So you need to have a sequence of observations, actions, and true states, which is a large restriction right now. I think future work should go into the direction of trying to do this without labels. Because yeah, it will be very hard to gather these state labels in a real setting, that's true.
Yes, over here, the blue microphone.
Hi, this is a question for the second speaker on the simulation to reality. So you listed 3 factors that contribute to the result you have. One of them being higher fidelity simulation. The second one is robust controller. Do you know like which one contributed most in your case? Because if it's just to bring up the fidelity, then I don't really see that solve the problem, because you can never go high enough. That's what I'm saying. Thanks.
So it's a very good question. So in our case, we find that the fidelity of the simulation, especially the actuator model and the latency, is very important. So without this, we actually have an evaluation in the paper. Without this part, if we just do robust control, it will never transfer to the real world. So this is like the essential part. But we cannot always increase, as you said, the fidelity of the simulation. For example, we're using a rigid body simulation, and we see some flexibility of the robot. We will not be able to incorporate this in the simulation. This is why we need another layer, which is a robust control, to help the transfer from sim to real.
Alberto, Orange Cube.
Hello? Yes. This is also a question for the second speaker, actually about the robust part of the control. So adding noise is an interesting idea, right? And try to make the controller robust to whatever noise you input in the simulator. But I can think of like hundreds of ways in which you could add noise to the simulator, right? Like from physical parameters to the simulation itself, to the kinematics, latencies. Like, can you give an idea of like where you add noise and how you add it?
Yeah, so we have two ways to add noise in this paper. One is to randomly sample the physical parameters, which like mass, inertia, and so on. But okay, the second thing is that we add perturbation forces so that we push the robot in the simulation. So it has to find a way to recover from different situations. There are other ways to add noise, or even you can have some adversarial training to increase robustness. But I want to emphasize that this robust control by adding noise is a double-edged blade. It will make the gate really conservative.
Okay, there's a question over there at the back with a blue cube.
Hi, this question is for the last speaker. Great work. I have two questions. First one is, do you know whether the EEG signals and EMG signals sort of vary from person to person? And the second question is, from your observation, is it possible that the robot was probably reacting more towards EMG signals over EEG signals, or the other way around, which means we can probably work with just like one sort of signal instead of combining both the brain and the muscular signals?
Yeah, great questions. So for the first question, the signals certainly do vary a lot between subjects, but you can see on average patterns that are consistent and that we try to classify. So for example, in the EMG signals, people will make gestures slightly differently. So on some people, you'll see antagonistic muscle activity a lot more than others. So sometimes you'll only see the inner forearm when you gesture to the left. Sometimes you'll see both. And the data augmentation helps to prevent like double classifications from a case like that. In the EEG, it definitely varies a lot, and the signals can be pretty noisy. So on average, if you look at a lot of trials, you'll see this characteristic shape to this error-related potential. But on individual trials and between subjects, it can certainly change a lot.
Okay, we can just take two more questions, then we have to cut this off. There's one more with a green microphone.
Hi, my question's for the prostate poker. I guess I have a couple questions. One is like, how transferable is this tool to other forms of cancer or to finding cancers in other organs, such as breast tissue? But also, like, is there something that's like particularly difficult about finding cancer in prostates?
I would actually say that finding cancer in prostates is easy, mostly because you don't need a robot to do it. However, it's a very standard model throughout it's used in lots of different surgical examples. It always has a stiff inclusion that you can very distinctly feel. And I would say, yeah, we've tried it on other organs. We're looking at livers right now, but we wanted to show it on a very curvy organ to show kind of extreme examples of normals. So for example, livers, you're not really going to be probing all the way around the liver. You're going to be staying on one semi-flat side. But there's lots of very curvaceous organs, like the kidney, that we also have looked at.
Okay, final question, orange microphone.
Hi, this is also a question for the prostate poker. I'm curious how this can be applied to other robotic systems, like continuum robots, for example.
Yeah, we should change the name of our paper to that. But I would say that we actually, with our collaborators at, in particular at Vanderbilt, they've got a continuum robot, and we're actively testing with user studies in future work with their continuum robots. We've also got a snake robot in our lab that we are kind of updating right now. So in the future, we'd like to do much more. The problem with continuum robots is knowing where they are in space. And so a lot of the telling it where to go and then poke right there is actually much more difficult. So there's a controls problem there that we haven't really dealt with.
So we have to cut this off here. We're running out of time. Thank you again for your good questions, and let's give the speakers a final round of applause.